Okay, right. Good morning, everyone, again. And I just want to recap where we are. So we've had a look at the Hammett equation. And the Hammett equation is simply log of your rate, your relative rate, and you plot it against sigma values, and you get a gradient, which is the reaction constant. And the way you work it is you'll have a reaction of interest, which is this reaction, where we've got an idea of what is the slow step in here, although we might revise what we've decided later. But you're provided with a whole lot of rates, or you get these rates from experiment, and you have sigma Hammett substituent parameters from tables, plenty of those. So we've got enough to work on to be able to do a Hammett plot. Problem is that these Ks here are not relative rates, they are actual rates, and so we're going to have to compare them all against the unsubstituted case before we take the logs. Should you just plot log k against sigma, yes, you will get a straight line, you'll get a free energy, linear free energy relationship. However, it won't pass through the origin in terms of the y-axis, so we must make that change. So I rearrange this so vertically. So I'm going to change this from being a horizontal table to a vertical table. So here we go, the sigma Hammett substitution parameters are over here. And so we've got our x values. Of course, our k's are not relative rates. I've just taken out the exponent and written out them out in full. We've got to divide everything by the unsubstituted system. So where the only substituent on the aromatic system is hydrogen, the unsubstituted system. And so we divide it all by 115. Once we've done that, we've now got a relative rate. And so now we simply need to find the log of that. And then if you've got the log of KREL, then you've got your y-axis sorted out. When you know your y-axis and your x-axis, you can plot your graph and you can get your slope, which is rho. Okay, so here we're ready. We've got our y values, we've got our x values. Note that we've passed through x is equal to 0, y is equal to 0. We pass through the origin. And when I plotted C, it passes through the origin because we divided everything by KH, such that on the left-hand side, we've got electron donating groups, and the right-hand side, we have got electron withdrawing groups. And of course, when we calculate the slope, we find it to be minus 0.5. And so our initial analysis of this is that the graph is negative, and so electron donating groups accelerate the reaction and electron withdrawing groups slow the reaction down. So this certainly does seem like a good choice of rate determining step for this entire reaction, given that we've got a negative slope. However, I'm going to throw a spanner in the works, and what we're going to do today is we're going to get some idea of what reaction constants look like. And when we have an idea of what reaction constants look like, we will have an idea as to whether they are large or whether they are small and how to react appropriately with them. So we might revise our assessment of this reaction based on whether that reaction constant is large or whether it is small. Okay, so here's some examples of reaction constants. And remember that I've said that if your reaction constant is negative, such as we saw attack of benzoyl chloride by anilines, if your reaction constant is negative, then electrons are moving away from the aromatic system, from the probe. If your reaction constant is positive, then you're receiving electrons, as we did in base catalyzed hydrolysis. In base catalyzed hydrolysis, we received electrons from the OH minus in the rate determining step. You might notice that there are slight differences in reaction constants to those we've encountered before, But just bear in mind that your reaction constants will change slightly depending on solvent and conditions that you have. Of course, if we plot acid dissociation as a reaction and get a reaction constant, you will notice that the reaction constant is 1, because what we're plotting is acid dissociation of benzoic acids against acid dissociation of benzoic acids. So we're plotting this reaction against itself. It is the reference, it is the standard, it's the reference reaction. It's used as a standard, and so if you plot it against itself, it's going to be 1. Now, I want you to have a look at these values for rho. And with the exception of this value over here, I want you to observe that the magnitude seems to be above 1. So that magnitude of that is about 1, that magnitude is about 2. These are large values. And you see this here is, it looks like an SN2 reaction with the O minus loss of electrons in the transition state. So it's a negative, it's definitely a movement of pair of electrons. And you'll see acid dissociation as well is going to be, yeah, so these values are large. This one is a small value, and we'll discuss why it is small. You'll see, have a look at the difference between acid dissociation as standard and this one. There seems to be something very slightly different. So these values, just remember that the values above 1, magnitude of 1, are large. These values are large and negative. These values are large and positive. This value is a small value, and there's a good reason for it being a small value. So in the Hammett equation, just remember that if you've got, it always passes through 0. So your origin is over there. When you plot it, just remember that if you've got a negative slope, we've got electron donating groups, make it go faster. And that means that you lose a pair of electrons in the rate determining step. And if it's positive, you've got electron withdrawing groups, make the reaction go faster, which means that you're going to be gaining electrons in the rate determining step. Okay. So this is a summary that if your reaction constant is negative, there is a loss of electrons away from the probe in the rate determining step. Electron donating groups aid this loss. Electron withdrawing groups inhibit this. However, if your rho is positive, it means there is a gain of electrons towards the probe in the rate determining step. Electron withdrawing groups aid this gain, and electron donating groups inhibit this. And in these two cases, we expect the magnitude of the slope to be greater than about 1. So for a negative slope, this should be less than -1, and this should be greater than +1. However, what happens if a magnitude is less than 1? There are 3 possible reasons that could give rise to a small reaction constant. The first one you will see is quite straightforward. When you see examples, you see why this is. That if your reaction center is far from the aromatic system, then those electron donating and electron withdrawing groups have little effect on the reaction center. And so that will result in a small change in rate or whatever value you're measuring as you change between electron donating and electron withdrawing substituents. Another reason why you could end up with a small reaction constant is that the reaction might involve both a loss and a gain of electrons. A third possibility is there could be an equilibrium in which there is a loss of electrons which precedes a rate determining step in which is a gain of electrons. And you see the combination of loss and gain contributes to a rate law which gives a very low reaction constant. So I want to show you an example. So have a look here. This is base catalyzed hydrolysis of esters. And if I take a whole set of esters, like paramethoxy, metamethoxy, metachloro, through to metanitro and paranitro, uh, uh, benzoate esters, and I look at the base catalyzed hydrolysis, as before, when I plot all of those on a Hammett plot, I'll get a large positive slope, and the slope will be 2.55. However, if I take these cinnamate esters, and I do the same thing, I have a whole lot of electron donating and electron withdrawing substituents, including the unsubstituted case, and I plot them all on a Hammett plot, you'll notice the slope is much lower. However, I've got the mechanism down here. The mechanism's the same. You've got OH minus coming in, you form that tetrahedral intermediate, and you've got loss of Eto minus, and of course the final equilibration. It's exactly the same in both cases. So how can this be that we have different reaction constants for the same mechanism? And I hope that you can see that this aromatic system in this case is very far from the carbonyl, whereas in our original case, the aromatic system is close to the carbonyl. And that has resulted in our reaction constant being its magnitude is less than 1. It is positive, indicating there is a gain of electrons in the rate determining step towards the probe. So if you're over here, here's your probe. Yes, this fragment containing the aromatic system is receiving electrons in this rate determining step. That's why it's positive, but it is small because this reaction center is very far from the aromatic probe that we're using to try and determine what's going on in this reaction. So that's really important, is that the first case is that we could have the reaction center being far from the probe. So the effect of the electron donating groups or electron withdrawing groups will decrease the further you are away from the aromatic system. So it's interesting to see how, let's see if we can have a look at a range of systems to see how it really affects the reaction constant. So I'd like to have a look, go back to acid dissociation and have a look here. At the top here, can you see this is our reference reaction? This is the benzoic acid, substituted benzoic acids plus water, and that's acid dissociation forming H3O+. So if you take this and you plot it against the reference reaction, you're plotting it against itself. So the gradient must be exactly 1. Right, so let's have a look now and see what happens if we introduce a CH2 in front. And you'll see that the reaction constant drops to half. Is now getting into the region which we know is very small. And same over here. So you can see over here that we've got, this is interesting now, we've introduced a double bond, and so we've managed to lengthen the chain, but without dropping the reaction constant below 0.5. So that's really interesting. That says something about the conductivity of that double bond and how it translates, or how it conveys the information from the electron donating or electron withdrawing groups through to the reaction center. And then finally, if we've only got aliphatic carbons between that, you can see that the reaction constant drops right down to 2. So having the reaction center far from the probe is problematic. And so it'll reduce the reaction constant. So you might end up with a very low magnitude of reaction constant because the reaction center is far from the aromatic system. Right, that's the first reason why rho could be small. The second reason is if the reaction involves both a loss and gain of electrons. And here are two systems. So have a look at this system. You'll see that in this case, you can see there's electron movement both towards the aromatic system and away from the system. So ask yourself this: will electron donating groups aid this reaction? Well, electron donating groups might aid this transfer over here, but it may inhibit this one here. And the opposite case, with electron withdrawing groups, the opposite could happen. It could disable the one arrow and enable the other. And that's why we are ending up with a low reaction constant. So when I look at this value here, I will say it's negative, meaning there's net movement of electrons away from the probe. But I note that it's small because the reaction mechanism involves both a loss and a gain of electrons. Another example is with the Diels-Alder reaction. So you can see if your probe is over here, you can see electrons are moving away and towards the probe. So you'll see that electron donating groups will aid this, but they will inhibit this, and electron withdrawing groups will do the opposite. So electron donating, electron withdrawing groups do not have a net effect on this reaction. And so this reaction constant is very low. So it's interesting in this case that the reaction constant is low because there is both loss and gain of electrons. But in this particular case, it has a slight negative value because electron density is moving from the HOMO of this diene containing the aromatic to the LUMO of the dienophile. So if a reaction involves both a loss and gain of electrons, then your reaction constant can be low. And the third case, why your reaction constant might be low, is if there is an equilibrium that precedes the rate determining step. So here we have an interesting case, is that your rate determining step is this step over here. And in this rate determining step, can you see that there's electron movement towards the aromatic system? And if there's electron movement towards the aromatic system, then we expect that the rho will be positive. Okay, so the rate determining step, we really expect a positive slope in the Hammett plot in this case. However, this rate determining step is preceded by an equilibrium in which there is a movement of electrons away from the aromatic system. And so this contradiction, this moving away and moving towards, means that your Hammett plot is going to give a small rho. What's happening is that you've got rate constants for forward and reverse reaction and rate constants here. All of these Ks, all of these rates contribute towards the overall rate law. And so there's contributions to the overall rate law from electrons moving away and electrons moving towards, such that your reaction constant is going to be very small. I want you to try and remember back to first year. And I wonder if you remember cases like this, where you have a fast equilibrium that precedes a rate determining step. And have a look at all those Ks there. Have a look at all the Ks there. And notice how all the Ks appear within the rate determining step, which means that if you've got an equilibrium with loss of electrons preceding rate determining step with gain of electrons, you've got both loss and gain contributing to the overall rate law. So here's another example. And I like this example. You can see it's got a very low reaction constant. I like this example because this example is hydrolysis of ethyl esters. We've looked at hydrolysis of ethyl esters before, and we got a huge positive rho of 2.55 for it. But that was base catalyzed hydrolysis of esters. This here is the acid catalyzed hydrolysis of esters. And you'll see that, of course, your first step in your equilibrium, you've got this electron pair that moves away from the aromatic system towards that H+. You've got that pair of electrons going away to the H+. So in your equilibrium step, you've got electrons moving away. However, in your rate determining step, you've got a lone pair from a water coming in. So you've got a gain. So in the rate determining step, you've got a gain of electrons, but in the equilibrium, you've got a loss of electrons. And this is reflected in the reaction constant being very low. This step cannot be rate determining because this involves a proton transfer. So can you see that a proton is transferring from H2O plus to HOH plus, and so that they cannot be rate limiting, and of course you very easily losing ethanol at that step. That's not rate limiting, and this again is a proton transfer. It can't be rate limiting. So these are the only steps that matter. You've got a rate determining step preceded by an equilibrium, but the equilibrium contributes to the rate law. So what we have, when you see a reaction constant that is small, try and look for one of three reasons as to why it could be small. The first reason why it could be small is if the aromatic system, the probe, is far from the reaction center. The reaction constant could be small if there is both loss and gain of electrons. And the third case why a reaction constant could be small is you might have an equilibrium involving a loss followed by a rate determining step involving a gain, or the opposite way round. Okay, so there are three reasons why you could have a small reaction constant. The reaction center could be far from the probe, or the reaction involves both loss and gain of electrons, or there's an equilibrium in which there's a loss or gain of electrons, which precedes a rate determining step in which there's a gain of loss of electrons. The equilibrium contributes towards the rate law. And so I would like to go back now to this reaction now. And first of all, can you decide whether the reaction constant is large or small? Would you be happy to say that that reaction constant is small? Its magnitude is less than 1. So this is a small reaction constant. And so let's try and decide which of the three cases it is. Would you say that the reaction center is far from the aromatic system? Here's the aromatic system, the probe. Is the reaction center far away? I don't think so. So that's the first case where we would have a reaction constant slow as if it's far, but this is not that case. The second case is if you have both a gain and a loss of electrons. I want you to have a look at this mechanism over here. If you're sitting over here, here's your probe. Is it right to say that you have a loss of electrons and a gain of electrons? Think about that. Yes, it certainly looks like it. So I might revise my whole conclusion by the size of rho here. And the size of rho is suggesting to me that there might be both a loss and gain of electrons in this mechanism. And if there's both a loss and gain of electrons in this mechanism, then the reaction constant is going to be small. Okay. Are there any questions? Okay. If there are no questions, please have a look at the problems I've set, and particularly where I've asked. So in the problems look, I'll ask you to comment on reaction constants. And normally when I ask you to comment on reaction constants, it's normally because they're small, and I'm trying to find out if you can find which of the three reasons contributes towards that reaction constant being small. Okay, if there are no questions or comments, as always, my email is open, so you can always contact me about the lecture slides, about the pracs. Please work through pracs if you have not done them, and contact me if you have any questions on all of this.